short talks. Sorry, I'm trying to admit people as I'm talking. I'm never good at multitasking. Okay. So yes, we're going to look at 3 different aspects of these measurements. So Eric, I think, is going to talk about some TROPOMI measurements over the UK. Neil is going to present about the new measurements that are going on in London, and then Daniel's going to briefly tell us what he's been doing in terms of modelling ground-based column measurements with NAME. So Eric, I think you're up first, right?
Yeah, I think that's right. Yeah, let me just share.
I guess I don't know if this was agreed in advance, but I assume each of you have about 10-15 minutes, then we'll have a little bit of time to discuss afterwards.
Yeah, that sounds good.
Okay.
Yeah.
Over to you, Eric.
Brilliant. Sorry. Brilliant. Is that? I assume that's clear. I'll just put that in full screen.
Yep. Yeah, we can see that.
Great. So hi everyone. I'm Eric. I'm a PhD student working in Heather Graven's group, and I'm going to share what I found when analysing the Tripomi methane retrievals over the British Isles. I'd firstly like to thank Anita, Heather, and Sudhanshu for their help and advice when I've been sort of going through analysing these data. So I'm sure I don't need to persuade you why we're interested in using the Tripomi methane retrievals. There are loads of good examples in the literature where Tripomi has been used to detect and quantify methane emissions from unpredictable events. For example, the very large sort of gas well blowout in Ohio in the Pandy paper, and this sort of previously undetected methane leak in Central Asia. Slightly more recently, the DeGao paper focused on retrievals over the US, looking at certain emission hotspots, mostly pertaining to the oil and gas industry. So just a quick brief overview of the Tripomi products. So we can see up until 2019, the spatial resolution was about 7 by 7 kilometers squared, and thereafter has been improved to about 5.5 by 7 kilometers squared. The retrievals are roughly daily, and the algorithm uses the full physics Remotech. There'll be a little bit more on that later. This study here by Laurent et al. Came out last year, where they were correcting the methane retrieval product for the surface albedo bias, something we'll see that's quite important later on. As we can see from this figure, that there are low sort of surface albedo column averages. For low surface albedo, the Tripomi retrieval seems to underestimate the TCON measurements, and sort of at relatively high surface albedos, we see that Tripomi column averages are overestimating TCON. And I'm sure we're all aware that as well that there seems to be quite a good comparison between the GOSAT retrievals and Tripomi, as well as the data from TCON and Tripomi, which has so far been analysed anyway. So turning our attention to the British Isles, we analysed the SORN products. I forgot to mention, for this research, I've been using the corrected methane product from the Netherlands Institute for Space Research, the SORN, where these column averages have been corrected for the surface bias we saw here. So we only retained pixels that had quality assurance values of 1, and then we realigned these pixels to a regular grid where each cell is approximately 0.15 degrees by 0.15 degrees. I realized that this does negate some of the high resolution benefits of Tripomi. I did experiment around with gridding the data at different resolutions, but I found, at least for this sort of initial analysis of the data, that this resolution seems to be most suitable for analyzing a large number of files. And we can always pick out the days that seem to have a higher pixel density and then increase the resolution for those days. So we looked at measurements between November 2017 up until October 2020. That's as far as the SORN product goes at the time when I was preparing this talk. We found there are about 12 days with a sort of high pixel density over the British Isles, so similar, not quite, so slightly more improved than the figure on the right, and then roughly 23 days with a good pixel density over the British Isles. So our pixel density is sort of similar to what we are seeing in this figure. For most of this research, I focused on the southeast in the UK and London. And there are roughly about 15 days with sort of a high pixel density and 10 days with good pixel density over the southeast. And this corresponds to about 2% of the retrievals being useful for the British Isles. And this low percentage seems to actually mostly likely be due to the cloud coverage over the UK. As I say here, the Remotech algorithm is designed for clear sky scenes. So Tripomi is rather a feat when it comes to analysing methane over the British Isles. So for the rest of this talk, I'll be focusing on London and the southeast. So as we can see in the 2018 National Inventory, there seems to be quite a high methane flux coming from London. And there is also quite a sort of significant gradient in methane between London and the surrounding southeast region in the UK. So one question we might ask is, well, how do the emissions, well, how does the CH4 gradient compare with the Tripomi retrievals? So this is the average of all the data across the south, or all the Tripomi retrievals from that period across the southeast. And the London area has been highlighted by this black box. And we can see sort of from this average that doesn't actually seem to be this gradient that we're seeing in the emissions inventories. It's just not, it's not there. We're not seeing these differences as, or at least differences aren't as large between the sort of southeast area and this London region. So there are perhaps a few other differences as well. We see actually the values over sort of East Anglia tend to be quite high. The values over urban areas seem to be kind of low. And as I said before, there is a smaller sort of gradient between London and the surrounding regions when compared to the bottom-up emissions. So what could be going on? So there are three things we sort of looked at the moment: the surface albedo, the aerosol optical thickness, and well, also, I mean, there is this lack of high density Tripomi retrievals, as I showed a few slides ago. And then, of course, there is also a possibility that the emissions estimates could be, you know, there are uncertainties in that, and perhaps the gradients aren't as strong as they are in the, as they are being shown in the national inventory. So for this, we're going to be focusing on the surface albedo and the aerosol optical thickness. So just comparing the daily surface albedo averages for London and the southeast, where the southeast region does not include London and is shown by this dashed red box, and then London is shown by the solid red box. And as I say, each of these points reflects a daily surface albedo average for these different regions. So we see there seems to be quite a good correspondence between the two, even if the surface albedos in the southeast are higher. And as we saw from the Laurent paper, even though these are corrected, the higher end of the retrievals tend to overestimate. Although there is only sort of a mean difference of about 0.03 between London and the southeast. And these values are fairly sort of towards the higher end, at least according to the Laurent paper here. So it's sort of around this region. So looking then at the aerosol optical thickness, this perhaps seemed to be maybe something that could also be leading to these to this lack of gradient, or why aren't the the averages across London as high? So again, we looked at the daily values, and generally, okay, there's a mean difference of about 0.03 between London and the southeast, and for the aerosol optical thicknesses below 0.1, there tends to be quite a good correspondence between London and the southeast. I say here where the AOT values are generally in the expected range, in the sense that, well, they're not going to be reflecting perfectly pollution-free scenes, which we might expect to be around here, but neither are they like high enough that we have really hazy conditions. So there are some days we see where higher aerosol optical thicknesses does seem to correspond with lower methane retrievals. This is a good example here from April 21st last year, where these two sort of really low methane regions correspond with these higher aerosol optical thicknesses. But similarly, there are also times when we aren't seeing any gradient, or really only small differences in the aerosol optical thickness, but still seeing quite sort of fairly large differences in the methane retrievals. So one thing we can look at is only considering some of these aerosol optical thicknesses that are much lower down, less than 0.1, excluding all of these higher ones. So this was just sort of arbitrarily chosen, mostly based on this figure here, where we can see most of the really higher ones tend to be over here in London. So there seems to be quite a good correspondence. So filtering out all of those days where the aerosol optical thicknesses was greater than 0.01, well, it only really led to quite small differences in the data set, and the average data set for all the years, as we can see from this figure here. So it still seems to be a bit of a mystery what's going on here. One possibility could be that maybe we need to look into the surface topology and see if there are any differences as a result of that. Or, as I said before, it could perhaps be down to a lack of data. Any suggestions on this are definitely welcome. So there are a few days that are worth perhaps investigating and having a look at, either in the simulations or with any sort of ground-based measurements. So I've just listed them here. There are a few sort of potential pollution events. For example, this one shown here. It potentially looks like there's something going on down here on this pixel between Heathfield and Imperial. And there are a few other ones that I've listed here. So yeah, in summary, we've been analysing the TROPOMI methane product, which has been corrected by the Netherlands Space Research Institute. Only roughly 2% of the retrievals from sort of November 17 to October 2020 are kind of useful for our research. There seems to be this discrepancy going on between the bottom-up estimates and the TROPOMI retrievals across London and the southeast. We still can't quite pin down what's going on or why this is the case. As I say, there seems to be quite small differences in the surface albedo and the aerosol optical thickness, and even then, when removing those higher aerosol optical thickness values, we're still not getting quite the same picture as we were seeing in the national emissions. So yeah, thanks for listening. Sorry that was rushed.
Great, thanks a lot. Any questions for Eric? Oh, Rob has got his hands up. Very good, Rob.
Hi, yeah, sorry, I'm really sorry. I came in at the end of that because I was running late. So you may have said this. Have you looked at the other data products, specifically the Bremen product? Because we're different, and especially in terms of coverage, but the data as well. And obviously, we know there's issues with the TROPOMI retrieval at the minute. So it's always worth having a second look, at the second product, because it's different.
Okay, yeah, we initially looked at the operational product and only this one. But yeah, okay, I'll definitely have a look.
So this, I mean, I guess everyone knows. So this product is the one that's kind of the pre-operational product, if you like. This is the one that eventually goes to ESA. So it's the same retrieval, but they've kind of done it's the early version that will eventually become the operational one. But the Bremen one is a very different type of retrieval, and in a very different way. And it depends on the application. I don't think we've quite settled on which one we prefer, and Hartmut or Paul might want to chip in on that. But they're different, and you may see very different things if you look at Bremen.
Okay. Bremen. Okay, cool. Thanks. Yeah, I'll check that out. Thanks, Robert.
Hartmut or Paul, did you want to come in on that?
I mean, I think it's probably still a bit early, right? I mean, it's always quite difficult to look at relatively small, amount of data, and because we know that there are all kind of things in the data. So I think I think you just need to be careful not to try to overinterpret things, just because somewhere something goes a little bit up doesn't always mean very much. There's still, I think the data is still, I would say that the data, there are still some issues, right? And it's not perfect. I think this is clear.
Okay.
Yeah. I guess, I think, we have to see it, but, certainly it's valuable to collect more data. And of course, UK being the UK is not doing you a great favor here with being cloudy all the time.
Sure.
Yeah.
Okay, thanks a lot. Alistair?
Yeah, thanks, Eric. A quick question, really. So you had the NAI map, and that showed a very stark difference in terms of, but I just wondered how stark that is. Is that just a sort of a plotting starkness that you would show up London much more strongly than the rest of the southeast, which has got lots of landfill sites, lots of cows, etc.? Are you sort of exaggerating that difference? And then my other question would be, in terms of if you did get a different emission over London, when you convert that into a column average, how much difference would you actually expect to see?
So yeah, those are good questions. So the first one, I guess, is that more down to like scales, right? Plotting scales and just trying to show those differences. So I guess for the national inventory, that was just that image I showed. That was just from the website on the interactive map. I just took a screenshot.
Yeah. I thought I saw it.
Yeah.
Yeah.
So I haven't really played around with the scales on that. We did try looking around in terms of the Tripomi retrievals, just trying to vary up that scale a bit, and even like considering really small ranges, and it just didn't quite want to show up. So I feel like, given how obvious that gradient seems to be in the emissions inventory, I don't know, perhaps you would expect in the retrievals you wouldn't have to play too much around with the scalings. That's my view on it. To your second question, I don't actually know. I haven't got around to do any of the simulations yet. Perhaps that might be something Daniel might be able to answer. I guess he's been focusing on that side of this.
Sure, thanks.
Yeah, I was...
Question to the experts: do we know how many tons of methane does London emit per year?
I can find out, but off the top of my head, I don't know.
I think it's about 2 megatons or something.
Sorry, Daniel?
I think it's about 2 megatons or something for the London area.
2 megatons, right?
Yeah. Something like 10% of the UK's emissions.
Now, let's do a mathematical problem. What would that be per hour? No, because most emissions for point source are given per hour. And most of the things that are detected by TROPOMI, they are like on the order of a ton per hour.
Yeah, I mean, I guess this gets back to Alistair's question about how much we would expect to see London in the column anyway. And I don't know if Daniel has that information, but I guess Mark might have that from his GeoSchem simulations, and I wonder if that's something Mark could quickly pull out and see how much that column average influences the that grid cell compared to the surroundings, and how big that is compared to the noise in the Tripomi measurements.
So yeah, I don't have any numbers off the top of my head, unfortunately. I guess, yeah, similar to what Harmer was saying, yeah, that's the only sort of numbers I can think of at the minute. Of the order of tons per hour is what, and that was kind of what was focused on in terms of, but that's in terms of point sources. So yeah, in terms of area sources, I'm not sure. I guess the wider the area, the more signal you'd like to you'd expect to see, but you might not see that directly overhead. I guess that's the other thing. Right? The wider the source, the more transport's going to play a part as well. And so you're going to have you can expect to see less of a gradient then between directly overhead of London and downwind.
Yeah. All right, we're going to have to move on. Pete, have you got a quick question?
I was wondering, following on Alistair's point, the maps from the NEAI probably just show the area sources of which London would stick out. But there's a lot of point sources around it, like landfills and industrial plants, which aren't within the Greater London area. So it would be more spread out than it appears on that map, I suspect.
Yeah, thanks for that. I mean, that's something we can certainly send you as a gridded figure showing all the sources together, if that's helpful. Right, anyway, thanks a lot, Eric. Neil, do you want to show us about the FSF measurements?
Yes, can do. I'll just get screen shares. Okay, that one. And then if I go full screen, does that look all right now?
Yep, that looks good.
Okay, good stuff. Great. So yeah, hello everybody. I'm going to just give a quick update on how the various ground-based remote sensing measurements over London as part of DARE UK project are progressing. So just with this first slide, I'll give people a little bit of an overview about what's involved in case you're not familiar with what we've been doing, what we've set up so far. So essentially, so the FSF is the field spectroscopy facility, which is a NERC facility. They're based up at University of Edinburgh, and they sort of own and operate various instrumentation for ground-based spectroscopy, and have recently acquired 3 sets of ground-based instrumentation for atmospheric remote sensing. So each of these different instruments measures different aspects of atmospheric composition. So for DARE UK, we've been working with them to install these 3 different instruments at 3 different sites across London. So in the map on the right and the infographic there, you can see where these locations are. So you've got a location in the southwest at NPL, which is National Physical Laboratory. Then in central London at UCL on top of their engineering building, and then in the northeast as well on top of a residential tower called Highfield Tower, which is in Romford. So about a month ago now, along with the FSF, we set all of these instruments up in weeks starting April 21st. So we've been taking data from these dates you can see on the left. So initially set up at NPL and then moving across to the other 2 sites, getting those up and running later in the week. And the instruments we have at each of these sites, we have the EM27 Sun, which is an FTIR spectrometer made by Brooker. That measures total column concentrations of greenhouse gases. There's also a Max DOAS instrument, which is sensitive more to kind of visible and near infrared wavelengths, and that observes sort of air quality and other trace gas column concentrations. And thirdly, we also have SIML sun photometers set up, which measure aerosols and scattering, which, as Eric kind of mentioned towards the beginning of his talk, sort of aerosol optical depth can have quite an impact on these like remote sensed atmospheric compositions. So it's really useful that we can have these instruments alongside our composition measurements as well. So yeah, you can see the 3 sites, they're kind of been picked to line up roughly with the prevailing wind direction, which typically goes from southwest up to northeast. So here's a bit of a closer look at the 3 site locations and some of the instrumentation involved. I'll see if I can get laser pointer up. Yeah, there we go. Okay, so I guess going from left to right, this is from the top of Highfield Tower, which is it's a 16-story residential building, and it's also probably at the highest point in the Greater London area as well. So height above sea level, that's for the actual instruments themselves. So I think at ground level, it's about 80 meters above sea level, and then the building itself is about 40 meters tall. And in the photo there, you can see this is the Max DOAS instrument, and you can see from the sort of the landscape, this is probably looking out towards the west. You can see it's quite a residential and fairly green area, actually, right on the outskirts of London, just inside the M25. So this is NPL in Teddington. So again, you've got your Max DOAS instrument here. This box here with the dome on top, that contains the EM27 Sun spectrometer. And in fact, the enclosure you can see here is something that was developed jointly between the FSF and University of Edinburgh to be able to operate these instruments on a sort of autonomous and continuous basis, because as they come out of the box, they're not really designed for this kind of thing. But yeah, this development allows us to just operate these instruments continuously. And then if we look to the right, this is our central London site at UCL at Torrington Place. And this is, you've got in the foreground here, this is the Simel sun photometer that we use for aerosol optical depth. And then on top of this pole here, we've also got an automated weather station just for, well, the pressure data is particularly important for our sort of greenhouse gas retrievals. It's one of the inputs for the retrieval code. So we use the data from our own MET station. But again, it just gives us an idea of what's going on locally as well. And yeah, looking in the background, you can see right in the middle of London, it's quite a built-up site around this location. So yeah, and we've just got here the locations, height above sea level. So anyone's sort of interested in those, I can pass those numbers on. So next slide, I'm going to focus from here on in on the EM27 Sun work. So on the greenhouse gas measurements. So I wanted to introduce quickly the sort of data processing chain, just because for the EM27 Sun, it's a bit more involved than for the other 2 instruments I've just talked about. So just to talk through this in summary, I think people who have been in the work package 2 meetings might have seen this already, but just to give a quick overview. So the data, as the raw data from the spectrometer, automatically uploaded to a central server, which is hosted at University of Edinburgh at the end of each day. And then we use processing procedures from the Karlsruhe Institute of Technology. So this is the research group that actually developed the instrument itself, and they've developed this data processing procedure to go with it through the Cocon project, and these procedures are all available, freely available online. And in terms of timeliness, we can sort of process a whole day of data from each site. Takes about 15 minutes. And the way the programs, the procedures are set up is that you basically run it across a whole day at a time. So rather than running it for each measurement individually, you do like batches of a day of measurements. So we're currently working on trying to automate this processing chain as much as possible. So we're currently at a point where, as long as we've got all of these inputs in place, we can just kind of execute the free procedures. We've got a Python wrapper which just executes one after another, kind of generates the input files, moves around and organizes files and directories, so that the output, so the output from the pre-processing goes into the inversion procedure, and similarly for this procedure which calculates the atmospheric absorption cross sections. So that's progressing quite nicely. The next step is really to try and automate it. So this can kind of basically search our data server for new data each day and kind of automatically run the procedures on that data. But I think that will be a little bit further down the line. But at the moment, we're able to process the data pretty efficiently. The other aspects we still need to look into, now we've started taking some data, which we'll see on the next slide, is implementing some post-processing quality checks based on various outputs from the optimal estimation code, like, for example, the quality of the spectral fit, like the forward model to the spectrum that we get. So to give an overview of where we are right now, we've processed data from all 3 of the sites up to the 16th of May. So, and we're currently, as I mentioned, working on the data quality criteria. So the plots show in the bar plot at the top, this is the number of successfully processed interferograms on each day. So this gives us an early idea of how much data we're able to get. So we can see, you might remember back to about a month ago, we had this week of like glorious sunny weather, and that's kind of reflected in the data taken at NPL. During that week, we get a lot of soundings because we have these clear skies without very much in the way of cloud cover. And then we can see the other instruments coming online towards the end of that week. And then on the bottom here, we've got preliminary total column concentration. So we've still, as I mentioned, got to check out on the data quality, but at least this already gives us an idea of like the density of measurements that we've been able to take, and things like the dynamic range of the different column concentrations. So we've got CO2, methane, and carbon monoxide from top to bottom, and the different colours correspond to the 3 different sites. So I mentioned timeliness of processing. So the thing that kind of holds this up, the reason we can't currently do processing kind of in real time, is we use these a priori profiles that describe the atmospheric state as the kind of starting point for our optimal estimation retrieval, and to be kind of as close as possible to the TCON sort of global ground-based network for these sort of total column retrievals. We use the same profiles as they do for that network, but these tend not to be available until 3 to 4 days after the measurement. But once those few days have passed through, we can run the processing without any issues. And there's always the option to kind of run a sort of dummy prior profile, or use a profile a few days out of date if you really wanted to get a picture of what's happening in near real time. But for like official data that we're producing, it would be a few days late. But yeah, that's just a quick overview. And as I say, we're sort of working on this at the moment, smoothing out the data processing chain, getting that as automated and as possible, keeping an eye on the data coming in, and just checking on the data quality, and yeah, that's where we are at the moment. So it's looking quite promising. Okay, that's it. Thank you.
Great, thanks a lot, Neil. Great to see some measurements from this project. All right, Alistair's already got his hand up.
Yeah, sorry. I suppose this is sort of answering the question that I asked Eric after his talk about what do we expect to see in terms of a difference in total column when you're in the middle of London, i.e. your blue dots, relative to when you're outside, your green and your orange dots. And I mean, quite small is probably the answer to that question. So just thought I'd point that out really. So, but yeah, great to see some data. It's fantastic. And also, sorry, I was also going to ask, how much of the day do you actually get data for? Because obviously these are daily data, but they're what, 8 hours or something?
It's it will depend on the time of year. So we take data from basically when the sun is 20 degrees above the horizon in the morning, around to 20 degrees above the horizon in the evening. So in the middle of summer, you'll get more data than in the middle of winter. And then the other factor, similarly for satellite measurements, is that we do need a direct sight of the sun to be able to take these measurements. So if you've got cloud in the way, then you're not taking useful data at that point. But I guess the benefit of the ground-based measurement versus the satellite is that at least you are observing continuously through the day. So if the cloud passing over is only temporary, then you'll start taking good data again once you've got clear conditions. So it means, yeah, we'll be able to get some data on most days, hopefully. Although again, through the winter, you'd perhaps expect there to be more cloud cover during the day. So yeah, we're getting into the time of year, sort of June, July, August, when we expect to get the most data.
And what's the time stamp of each measurement? I'm dominating the questions here. Apologies, Matt.
No problem. So each measurement, it's a measurement every 75 seconds or so. So the temporal density is pretty good.
Brilliant. Thank you. That's great.
Okay, thanks, Matt.
Yeah, thanks, Neil. Great to see these data already out there. So fantastic. Thank you. I'm a bit ignorant of XCO2 time series. Just explain to me the what looks like a build-up in XCO2. Is that during the day that rises?
Yeah. So what you can see with these blotches, I suppose, for want of a better word, is it's like the variability through the day. So so one element of that will be kind of the natural cycle of CO2 through the day, and then superimposed on top of that will be the contributions of any emissions like upwind of each site, basically. So what you're seeing is like a superposition of the two. So it's hard to see from this plot that we do have, because we are measuring throughout the day, as long as there's no cloud cover, we do have the possibility to look at variation during the day and try and sort of untangle these two components. I think you might get kind of like the background variation, but then you might see sort of, especially in the CO, I'd imagine, where you get, if you've got sources, you get quite dramatic spikes compared with the other two species shown here. So they'll be kind of folded into what you can see here as well. But we've got that, possibility to look into, what influence does time of day have on the concentration, the pollen concentrations that we see.
Yeah, I think you might want to be slightly careful. I think there is, with these, especially for large angle, there's also always a risk that spectroscopy can introduce some artificial trends throughout the day. Although there is some correction applied, there's probably certainly some work that still now needs to go into that one to really make sure, that it's really the diurnal cycle and not some air mass factor dependency.
Yeah. So this is why we already cut out observations where the sun's below 20 degrees above the horizon, just because you can't be confident the air mass is being corrected for properly there.
All right, thanks a lot. Oh, I saw another hand, but it's gone.
Yeah, sorry, Matt, that was mine, Mark, but Hartmut just answered my question, so that's fine.
Great. Okay. All right. Any other questions for Neil, or should we move on to Daniel? Okay, thanks a lot, Neil. Daniel, over to you.
Yes, hello. Let me just get this up. Yeah, that should be live. Great. So, yeah, I'm Daniel Hoare, University of Bristol. I'll be talking about some of this kind of work on, as mentioned, modelling some of these column measurements that we've just seen. So the work I'm going to be presenting today is some kind of, it's preliminary work, it's more proof of concept. So this process isn't yet in like an operational stage, but this was just, going through some of the technical details and getting things set up. And then hopefully over the, now that the measurements are set up and running, we can move this to the operational stage and really kind of compare the two. But yeah, so I'll be talking about some of the modelling process itself. So a bit of context of where I'm coming from. So I mostly work on the London greenhouse gas network, which is the set of in situ sites across London. So we've put in a bunch of new LICOR sites, and there's already some existing Picaro sites around London. And the keen-eyed members of the audience may recognise that two of the sites here are two of the sites from the last presentation. So we've got Highfield Tower and MPL have both the in situ and our the FSS column instruments in there. So that'll be a really interesting point to do some comparison, both in terms of the data, but also how the modelling from the same point differs between the column and the in situ point measurements. So that'll be interesting. And yeah, one of the things I'm interested in doing this modelling work is that a lot of these sites, because they're in London, they're very affected by very local emissions within London. And hopefully some of these column measurements see a bit more of a spread out area by virtue of being column and taking data from slightly further away from the surface. So that's where I'm interested in this. So if you move forwards to the modelling itself. So the way we're modelling this is adapted from the existing process used for things like GOSAT measurements in the past by Anita and other members of the Bristol group. And essentially the way this works is that you split your column measurement up by the different levels, generally the ones used in the underlying data to make things simpler. And essentially we do a separate name run for each of these different levels. So each of these different levels is treated the same way to start with that we would for a single point in situ site. And then once all these have been run, we combine all of these different footprints together into a single column footprint. So that's the simple view of it. Now, the problem here is, as with everything, the devil's in the details, and it's that last step where things get a little bit more complicated. There are, of course, other modelling concerns. So there's issues, for instance, for the maximum height that name can run at might not be the same as the maximum height that goes into the data for the column product. You also have to worry about computational details. Like, you don't expect the higher levels to contribute as much to surface sensitivity, so you can, lower the amount of computational resource used on them by using less air parcels in the models and trying to fine-tune the balance between computational efficiency and also accuracy of the resolving thing. But that's all fairly simple compared to some of the other details involved in this sort of modelling. So some of the complexities that go into this is that the column measurements are, as we have seen from the previous presentation where we had that lovely diagram of all the different things that go into turning a retrieval into a number is that a lot of these things can also affect the way these are modeled. So obviously in the modeling, we have to account for things like angles of the sun. In this kind of test modeling that I'm doing, I've ignored things like cloud cover and stuff. So some of the graphs I'll show you later will be assuming perfect sunny weather. You also need like things like, you know, like I said, in the model height, you need to know the different pressure weightings. You need to know the sensitivity of the column to the various levels in order to correctly put all those levels back into a single measurement. And there's just a lot of details that go into this. You also want to make sure you get it right, otherwise you can end up with unusual numbers in the output. And there's also the process that, like with processing the raw data into a value for the mole fractions, there's also a lot of steps that go into then processing the numbers that come from that into a footprint itself. So the output of the raw data we're given then needs to be converted into a format that can be processed by name. We then run the name model. We have to get the output from that. And then there's extra steps to convert, like I've said, that multiple different footprints into our single final column footprint. But once we've got all that done, we can start looking at some of the preliminary results, numbers to be taken with a pinch of salt and all that. So here are some time series from some initial runs. So the top graph here is for a EM27 instrument, NPL in southwest London, and then some actual data from now this one's model data from Thames Barrier site in central London. So we've got the orange here is the total mole fraction methane ppb according to the model, and that blue line gives you the background level, which for us is essentially a box that surrounds you know, over nearly to America and to Russia on either side. So this is things that are completely unaffected by any London or UK emissions. So there's a couple of things we see here. So if we quickly look at the Thames Barrier one first, you get that fairly flat baseline because things don't change much over this month timescale, and then you see this kind of daily spikes where, you know, during the night time you get boundary layer effects at the surface, and you see these giant increases in emissions because London's quite a lot of source of methane there. So you'd expect that as the boundary layer decreases, you get these big spikes. So if we look at the EM27 model instead, we notice that the background for this is not flat at all. One of these key features is we've got this kind of dash upwards. And again with this model, so this is run, I believe that I ran this between 8 AM and 8 PM each day. So as we've just heard, when you get low levels of sun, you have to be extra careful because of angles through the atmosphere and stuff. So take the ends of each of these days with an extra grain of salt because of those considerations. But we do see this kind of dashed line effect that we saw from the actual data just presented. But it's interesting to see that according to the model, a lot of this comes from the background input, which implies there's something kind of large scale physicsy happening, as opposed to being just a result of emissions build up during the day, for example. Although if we then go on to the next slide, where this is just the enhancement. So this is the difference between the background and the total value. So for this is most likely due to local emissions. So we can see, again, we have the Thames Barrier and the EM27 Sun, two measurements again. And again, you do see, now we see if we look at Thames Barrier first, you do see these big lines now going down rather than up. And this will be because I've filtered the Thames Valley data to the same timescale as the EM27 Sun, and this will likely be due to, again, boundary layer effects. So at the start of each day, it's got that nighttime high, and then as the sun warms up and the boundary layer increases, the concentration we see goes down, which is why for the Thames Valley, we're going to get this slope downwards. And then for the EM27 Sun, we got a much flatter curve, which again, I think you would expect to see, because as I said before, because of the column measurement, we would hope to see a wider view of emissions, so we're less affected by those very local London emissions, and maybe seeing more of a kind of a broader picture, so kind of the emissions get flattened out a bit. But you see kind of the long-term trends, like the weekly cycle of the two seem to follow, which again you'd expect to see. So that's kind of probably the large-scale weather patterns. But you see that there is a fair amount of enhancement seen. So obviously, as you'd expect, the column measurement sees a lower enhancement than the site in the middle of London at ground level. But we're still seeing, you know, on the peak days, a 20 ppb enhancement over the background. So this will be the total enhancements. This will be for London emissions, but also UK emissions. And depending on the day, you'd expect, you know, approximately half of that to be London emissions compared to the rest of the UK for a in situ site. I can check, haven't done the numbers for yet what it is for the EM27 measurements, but I expect it to be, you know, somewhere within the same range. So that's the kind of enhancement that I would be expecting to see. Be interesting to see how that works when we start running more footprints and start comparing it to the real data and start teasing out some of these cycles and patterns and stuff. But that's the kind of very preliminary 1 month of data runs I've taken a look at. Going forwards, hopefully we'll get this to an operational stage so we can start running in near real-time footprints for the 3 EM27 Sun installations. We can start comparing those to the in situ observations, and then I'll start working on some inverse modeling work where we compare and see how much extra skill we get the model to have getting London's emissions by adding these column measurements to the existing in situ measurements. And that's my update. Thanks for listening.
All right, thanks a lot, Daniel. So it's really interesting to see that a lot of that diurnal variation in the EM27 comes from the background. So
yeah, that's not what I was expecting to see, but that is apparently what we see. So
is this due to the fact that you're seeing different vertical levels in the atmosphere at different times of day then, or something? Or is this something we need to look into a bit more?
Yeah, I don't want to conclusively say anything about looking more into it. I have had a brief look, and I didn't see any smoking guns, which was like, it was like, oh, it's obviously just X. So it could be a combination of a few different things all leading up to it.
All right, thanks. Any questions for Daniel? Alistair again.
Seem to always ask a question. So yeah, this diurnal cycle. So I mean, there have been aircraft campaigns where they've flown, you know, vertically upwards during a day and stuff like that. Do they see this? I mean, it just looks, I mean, is this just venting of surface emissions getting up higher? I mean, I just can't see how that would work. Yeah, I'm struggling with that one. So, but comparison with aircraft might be something to do whether they see a similar pattern of increasing concentrations then as the day goes on vertically, because that's what it's implying, isn't it? Is that right? Am I reading this right? As the day goes on, the concentration rises.
Yeah, so we're seeing the concentration rising, but we're seeing it mostly from the background.
But
So
then
this will be our, so I'm using the same name domain as we would for any of the other stuff. So that's the contribution just from that kind of giant rectangle.
Within a day, I can't see how that would drastically change. Can you?
Yeah. It was, I was not expecting to see that.
Yeah, I'm equally surprised. But Matt, have you got any thoughts?
No idea. But I think it's clearly something we need to investigate. But it looks very similar to the data. So
Yeah. I'm not discounting it, but maybe the aircraft would help us with that, because they must see this then, surely. I mean, this rise day in, day out of, if they fly for 4 hours during a day and they're doing vertical profiling of, in the morning and the afternoon, surely that happened in gauge. Did they see more methane in totality than, or is it much higher than that? Is it much higher than the aircraft goes? I mean, where's this coming from? Can we break it down by height at all?
We could probably look at the influence of the different levels, the footprints released at different levels, and see if there's a change throughout the day of which ones are being more weighted. Here, Mark's going to explain it to us. Go on, Mark.
I'm not sure I'm going to explain it. It's more a question of, is this the column that's directly overhead, or is there, is there a change in angle basically during the course of the day? Could explain some of it.
So for this just test run I did, this is just the footprints are all calculated vertically. They're not offset to the correct angle of the sun, which is why I'm dubious about the endpoints. So it should be fairly accurate for kind of, central overhead sun. But even in that kind of central area, you still see this strong change.
Would it be the height of the actual column that your modelling is changing as the day goes on?
Tell you what, I think we've run out of time, but I think a few of us are going to get back together on Thursday to talk about these things. Has anyone got any last questions for Daniel or anyone before we finish?
So, Matt, I have another meeting in my calendar for Wednesday morning. I assume this is not taking place, right?
Well, the plan was, I think Anifa can correct me if I'm wrong, but the plan was for today that we were going to have a more general interest set of talks on these measurements. And then Wednesday was a time for us to actually, for those of us who were hoping to work on this stuff, sit down and start planning what each group is going to do and how we can work together on it.
So you think there's actually a point having a meeting again on Wednesday?
Well, I'm happy to hear what other people think. I feel like it'd be worth having at least 15 minutes to sit down and figure out what everyone's near-term plans are. But I also understand that everyone has a lot of meetings. What do you think, Humpage?